Hey everyone, thank you very much for coming. Today we get a privilege to welcome Huib van Langevelde, Professor Huib van Langevelde. And maybe let's start with image. I think everyone knows what is that thing in the right corner. This image, I'm not really sure if this one, but the first image of this thing released in 2019 marked an immense effort for 100 years searching actual black holes that are going on. And today we get the opportunity to invite a speaker who was present and active part of the team working on the 7th Horizon Telescope on this giant collaboration of 400 scientists, and currently is director of the whole project. Ladies and gentlemen, Professor
Van Langevelde. Yeah, okay. Thank you. Great to be here. Great to be here. Nice to be in Cambridge. Yeah. So let me introduce myself a little bit more. I think that's useful for early career scientists like yourself to understand that. My official job title is that I'm the chief scientist at JIVE. JIVE is the Joint Institute for VLBI in ERIC, which is a European legal entity for small research collaborations. And that JIVE operates the European VLBI network. And I hope you've seen the Cambridge 32-meter telescope, part of Merlin, part of the EVN. I run a telescope for you. That's basically the message there. I'm also the professor of galactic radio astronomy in Leiden. Claims to be the oldest astronomy department in the world. And I have an affiliation in New Mexico where I spent my time as a postdoc. And as mentioned in the introduction, I'm the project director of the Event Horizon Telescope, a 400-person collaboration, and everything you see today is very much a team effort. So I'm going to talk about the Event Horizon Telescope, which is a collaboration that aims to resolve what happens at the central supermassive black holes of active galaxies and our own galaxy. And the key ingredients today will be studying the non-thermal, optically thin synchrotron radiation that comes from the vicinity of these supermassive black holes with extreme resolution. And we have two of these, one monstrously large, M87 in the Virgo cluster, and one in our own galaxy, a mediocre supermassive black hole, but very close. And this whole thing was revolutionized in 2017 when the ALMA telescope in Chile was added to our array. Okay, so maybe I should just start with the movie that we showed in 2019 to the politicians. Well, the few politicians that were coming over to our presentation, most of them were at that time concerned with the Brexit. And this is the movie we showed on the occasion. The movie starts, good dramatic music, at the high altitude plains of Chile, where the ALMA telescope is based. And it zooms in to the brightest radio source in Virgo, Virgo A. Here you see in color the LOFAR image of that telescope. You can also see it from the northern hemisphere. And if you zoom in with higher and higher frequencies and longer baselines, the music is a bit dramatic. And you zoom in even further, we were able to show this. And we claimed that this was the first ever image of a supermassive black hole, the first image ever of a black hole. That's not really quite true. It's really the image of the shadow of a supermassive black hole. And since that in 2017, since that presentation in 2019, from the 2017 data, we've also published the other supermassive black hole that can be imaged like that, SgrA star. And in the meantime, we've gone over and have now 56 papers out with 20,000 citations. And for the M87 picture, we assume that about half of the human population have seen that image. and heard about supermassive black holes. So this is all about radio astronomy, and radio astronomy came late into play. Carl Jansky, very low frequency, built a receiver to pinpoint where the noise that they had on transatlantic communications was coming from, and he found out that it came over this telescope with the regularity of the galactic center. That was met with lots of skepticism, because at the time people knew that the universe was full of stars, and if you look at the optical sky, you see stars and you don't expect that much radio emission from the sky. What he detected would require a gas at 10,000ths of kelvins to be present on the sky over areas as large as degrees. And of course, stars are just very tiny things. So in the course of the years, that got better, and a lot of radio sources were identified. For instance, this is an image of the Virgo cluster, and almost all of the light that you see in that image, which is a wide field image in the optical, where the bright foreground stars have been blacked out. All of that image is starlight, so made in fusion in the interiors of stars and coming out as black body radiation. Except, and you can probably not see it, there's a little wisp here, and that's actually the jet of M87. This galaxy, the biggest one in the Virgo cluster, harbors the radio source Virgo A, and it's also Messier's 87th catalogued nebulosity, which was not a comet. That's why he made this catalog. So I'm now curious, who is my audience? Is this all? You're asking questions when I say things you don't understand at all, right? Great. So the radio sky looks quite different. It's full of dots. This is a empty field or just an arbitrary piece of the sky made with a Loeffler telescope. And these are not stars, because there's no Milky Way you can see this in this image. These are all radio sources as cosmological distances. Very few galactic radio sources are known. There's a couple in this picture over the Green Bank telescope in the US, supernova remnants, H2 regions where stars are being born that ionize their surroundings. They may produce some radio emission, but the sky is dominated by sources at cosmological distances. And that's because I've sketched that already. You won't see stars. By the time you go into the radio, stars, you are on the early gene scales of the Planck curve, and stars will emit very little in the radio by their thermal emission. But at the far end, at the lowest frequencies, synchrotron radiation kicks in, which is produced by relativistic electrons accelerated by magnetic fields. And there's a galaxy like that, that's M82, a starburst galaxy, has a lot of optical, it has a lot of infrared, and then it has a lot of radio emission coming out in the frequencies under 100 gigahertz. And of course, this place here has a long tradition in radio astronomy, and I have to acknowledge that. You're laughing because Westerbork is moving, not because you see the Cambridge telescope and it makes you happy. Okay, so this is a long tradition in radio astronomy. The Cambridge interferometer in the middle, the Westerbork telescope close to where I live in Drenthe, the VLA in New Mexico. Now we have ALMA, millimetre telescope, from a worldwide collaboration in Chile. And we are all looking forward to the square kilometer array being built in the southern hemisphere. So I always show this slide in my course when I teach radio astronomy in Leiden. It was clear that the sky was full of radio emission, and things like Cygnus A were identified to be radio sources. But with a single dish telescope, you cannot resolve any of this structure. It required interferometry, pioneered here in Cambridge, to resolve it into these two blobs. And now we know that Cyg A really looks like this. There is two enormous lobes on the sky producing radio emission, and all of that seems to originate at a very tiny location in the center, and that location in the center usually coincides with a fairly distant elliptical galaxy, which when I started doing my research, my astronomy career was still quite a mystery how these things could come about. Because if you have a thing this distance in the universe and this large on the sky, it means that enormous amounts of energy must be created over a very long time. And this AGN energy crisis requires that about half a solar mass per year is turned into energy with a very, very high efficiency. And people have studied active galactic nuclei since, and there's a whole family, there's a whole zoo of possible configurations, quite often related to how we look at these. Some we look down the throat and we see very bright compact sources, and for instance, we know that this source must be quite close to the plane of the sky. Presumably this one in the west is coming a bit out of the blackboard, because the jet is brighter on that side, and because of the way synchrotron emission works, you get a beaming and you get brighter emission from things that come towards you. Are you still with me? Some people not. Okay, great. So this is usually where I have a few slides explaining black holes, because that was one of the possible explanations how these things could occur. Because if you want to generate that much energy from something that's so small, it has to be extremely massive not to be blown to pieces. And so supermassive black holes were proposed as the engines for these active galactic nuclei. Now, in the 50s, apparently it was necessary for somebody who was writing comics to make this little excursion to introduce black holes into the story. Of course, that's now unthinkable that a trained Starfleet commander would not know what a black hole is. And so I also assume you all know what a black hole is. Yeah, I see a few people not. Okay, and black holes are for real, right? When I did my studies, this was hypothetical, but for now we know that black holes exist for sure. Not just from these enigmatic active galaxies, but there's also some galaxies where we see gas in rotation quite close to the nucleus. We know some stars that have massive companions that we cannot see. There are other clues for black holes. There is the galactic center, which I will visit later. And of course, now we even have the gravitational wave events that demonstrate that black holes must exist. Nevertheless, it sounded like a good idea to try to resolve what is really happening at the heart of these supermassive black holes. And some people made predictions what you would see. This is, for instance, to the left is the gravitational lens black hole that was used in the movie Interstellar. That's what the gravitational lensing would look like for a thin accretion disk around the black hole. So you're seeing both the front and the back at the same time because the gravitational field is so strong that you get lensed from the back. And my colleague Heino Fouke in 2000 predicted that maybe you could get VLBI to such extreme resolutions that you could resolve a supermassive black hole in either our galaxy or a relatively nearby galaxy. And the predictions are that for such a star, the Schwarzschild radius, the radius around the black hole from which nothing can return, would map to something like 10 micro arc seconds. So 10 times a thousandth of a milli arc second, which is a thousandth of an arc second, which is a 60th of an arc minute, which is a 60th of a degree. So something really, really, really small. And for M87, the prediction was not so clear because we didn't know for sure whether there was a 3.5 times 10 to the 9 or a 6.5 times 10 to the 9 solar mass black hole in the center of M87. So to do that, we have to deploy very long baseline interferometry. And I will not assume you know how that works, because I don't think you have been exposed to that, but maybe that's not true. So in radio interferometry, what we do is we correlate the digitized signal that is received by two telescopes after compensating for the relative delay. And if you do that properly, then you can measure a correlation function between these two telescopes. Don't ask me where the photon went, because this is really in the wave regime. So we can digitize this incoming wave at both telescopes and do the detection later in the correlator. And if you do that for many telescope pairs, it turns out you're building up the Fourier the Fourier transform of the image on the sky. Every one of these telescope pairs is sensitive to a Fourier component that is inversely proportional to the distance between them. Fourier transforms, yes, right? Yeah, okay. And I'm not going to write it up. And even greater is that while the Earth is moving, you're doing this Fourier sampling of the same distance, but on different angles on the sky. And so if you do the extreme of that, it's called VLBI. You have no cables between the telescopes. At both telescopes, you have a clock, a very, very accurate clock, and you write the clock ticks together with the digitized data on magnetic media. This is a very old slide. This is when we still use tapes, but nowadays we do hard disk, or we just pump the data over the internet, and we build up in the correlator the Fourier components that will make the image. And you can get fantastic resolution. That's an image of the 126th source in the third Cambridge catalogue. I'm bluffing. The 120th source in the third Cambridge catalogue. And it's been tracked over the years. And it's one of these AGN, so at the origin of the variability is probably a supermassive black hole, and it's ejecting stuff into the surroundings, and we can track it over the years. The time is ticking on the top, and these images can be made with VLBI. And the resolution is also on the graph. It's milli arc seconds, which means that this is like determining whether a tennis ball is in or out, like you do with a Hawkeye system. And you do it for Wimbledon, but you put your Hawkeye system in New Mexico, US. That's about the angular resolution. Well, that would be great. Why don't we do VLBI of everything? And there unfortunately are some caveats. I've talked about that you get these Fourier components, so you have to deconvolve the fact that you have a lot of spatial frequencies missing in your image, so that's really nasty. But most seriously is that you can only do this for things that are extremely bright, for things that have very high flux coming from a very small piece of the sky. We usually do that in brightness temperatures, and you see that we're making a telescope as big as the planet, but we're only using 25-meter holes where the light can come through to cover that whole Earth-wide telescope. Okay, so we're going to do that in order to zoom into supermassive black holes, and therefore we had to do the extreme. And the extreme is to use telescopes all over the planet. Then you have the longest baseline. The diffraction limit is set there by lambda over b, so the wavelength over the baseline length, the separation between two telescopes. And you get the best result if lambda is small, so very high frequency, and b is large, so very long baselines. So we do that by using telescopes all over the world that are sensitive to just the edge of where we can still do radio astronomy, and that edge is set by the atmosphere. So when you come short of millimeter wavelengths, the atmosphere has so much molecules in it, which have very pressure broadened profiles, that only on very, very high and dry places you can use sub-millimeter techniques. So we have telescopes for sub-millimeter astronomy in places. There is Pico Valletta and the Plateau de Buur interferometer in Europe. We have our own JCMT, or we used to have it used to be our own JCMT on the summit of Hawaii. We jointly operate the ALMA telescope, but also places in the US and on both Arctic and Antarctic poles are dry and high enough that we can do millimeter VLBI. Oh, here is a nice array of telescopes. So this is the one, this is the one in Pico Valletta in Spain. In fact, you can go there and ski. That's the one that's really accessible. This is the ALMA telescope. You have to be very lucky if you can get a visit to that. This is the LMT in Mexico. You have to be very brave to visit that one. This is in Arizona, in Kitt Peak. This is at the summit of Hawaii. This is the SMA and then the JCMT. And this is the one you never get to see. This is the telescope on the Antarctic. And we went out there for the first time in 2017, because that was when we had cleared with the ALMA telescope that we could use the ALMA telescope in this ongoing millimeter effort. We went through all these telescopes and made sure they were all looking at the same sources at the same time and recording the same frequency bands from the sky. You see me at the ALMA telescope? That's actually a lie. I was not there during the observations. And if you think I look pretty bad, I was feeling even worse than I look. I just put down my oxygen mask for this photo, and afterwards the site technician says, well, we're going to take you to the infirmary and you have to lie down for half an hour now. But at least I've been there.
What's the elevation?
Huh?
What is the elevation?
So that's 5 kilometers. So yeah, it's quite demanding. But people that go there often, they get used to it, or they know how to behave. Okay, so all these telescopes, I want to stress, are usually built for something else. They are there to do molecular astrophysics, star formation, maybe molecules in the far universe, planet formation. And all these telescopes have to be rewired, including ALMA, to do our EHT experiment. And in addition, we have pushed the limits of the digital equipment and made sure that we record much more bandwidth than we can normally do in VLBI with these EHT stations at these very high frequencies. And it's all people work and requires a lot of dedication. For instance, the guy smiling in the middle, these are the South Pole operators. They have to winter over at the South Pole station to do the experiments, and which includes hours. And then it goes all to a central correlator data processor where it's combined. So let's go back to what I did in the beginning. That was M87. So here's a blow-up of M87 or NGC 4486, the loudest radio source in the Virgo cluster. And here on this photo you can see the little jet, already known in the beginning of the 20th century, which is not starlight, but this synchrotron radiation coming out even all the way in the optical. This is how the Very Large Array sees Virgo A, and from that you can see that the jet is blowing in our direction because it's very much single side brightened. So we see in VLBI images we don't see the counter jet, and that's because it's basically almost beaming directly at us. And if there's a black hole at the base of that, you can imagine its orientation must be perpendicular to the jet direction. So this was the best image we had at the time, at 22 gigahertz, so at 1 centimeter, and we were going to do the experiment at a submillimeter. So this is what the raw data looked like. This is the data in the Fourier space. So this this rectangle in the at the left is what we call the UV plane. It's basically the projection of our baselines onto the length scale plot. So things that are far apart go to the outside, and baselines that are short go to the inside. And at every of the color points, we measure a complex correlation function. So I'm challenging you here a bit, because usually it is a full semester, maybe 1.5 semester, to master Fourier optics and then radio astronomy, radio interferometry. And this is what a one-dimensional summary of that data looks like. So now I've plotted in the same colors the distance in Fourier space and the amplitude of the signal that we see. And if our source was a point source, it would have the same response on all physical scales. If our source was a Gaussian, it would have a Gaussian response in this graph. But what we see is something with two minima and experienced radio astronomers will immediately figure out that that's the sign of a ring on the sky. And to convince ourselves, we actually did the experiment over 4 different days, and we found more or less the same result over the 4 days. So I already showed you the dramatic movie, and this is what we got out of M87 again. This image is consistent with one of the 2 masses that was, it doesn't seem to like to do this. Okay, now it does, but I have to be here. Okay, one of the 2 a priori known masses of 6.5 times 10 to the 9 at a distance of 45 million light years. I said the observations were at 1 millimeter, 230 gigahertz. The equivalent temperature of this is 6 10 to the 9 Kelvin, and this thing measures 42 micro arc seconds on the sky, which is the same as 700 AU, so the size of the comets in our solar system, but then at the distance of the Virgo cluster. Now, before I'm going to do the interpretation, I'm going to do the other source, SgrA, because SgrA is actually the more fundamental result for the interpretation. So beforehand, actually, we thought we were after SgrA. Beforehand, we thought that SgrA was the brighter source, and it had the larger image on the sky. We think that we knew beforehand from, for instance, the calculations that I showed for Falke, that the shadow of a supermassive black hole is about 10 times its gravitational radius, which is basically gm over d c squared. So basically it scales as m, the mass of the black hole, and the distance. A bigger black hole gives you a bigger shadow, and a more distant one a smaller. And we thought beforehand that SgrA was the more obvious candidate. So let's have a look at SgrA. SgrA lives at the center of our galaxy. You cannot see it in the optical because in between us and the galactic center is all this interstellar dust, because we live some 10,000, some 8 kiloparsec away from the center of our galaxy. And if you make a radio image of the brightest radio source in the Archer Sagittarius, it looks like this. And this is a beautiful image taken with the new Meerkat telescope in South Africa. And you can see there's something bright in the middle, and it's full of all these filaments and bubbles. This bubble is a supernova remnant where a star once exploded, but all the filaments are indicated of large-scale magnetic fields, which accelerates electrons to get the bright emission. And in 2020, we have known and suspected, and actually known that there is something dark and very massive in our galactic center. Maybe it was already proven that there is a black hole there, because we can see in the infrared the stars go around the galactic center. And my colleagues, Reinhard Genzel and Andrea Gates, got the Nobel Prize for making that observation. And the cool thing is that by making these measurements, we know not only that there is something supermassive in there, but we actually know the mass. And also because the motions are the 2D projections of 3D motions, we know the distance to the galactic center very accurately. So here we already know m over d, and so we can do a very precise prediction of what the size of this black hole image should be. Now, why then did you do M87 first, and why did you confuse the people in Brussels from the European Commission with your M87 result when SgrA was the more fundamental? There's two reasons for that. The first one is we have extreme interstellar scattering towards the galactic center. People have been trying to image the galactic center black hole candidate, which is very bright in the radio, for decades, moving up in frequency all the time to get better resolution. But all the time we got a blurred image, because in between here and us, the dust doesn't block radio waves, but the free electrons scatter the radio waves and blur the image. So that was one reason why SgrA was difficult. But the other reason it's difficult is because it's like trying to make a picture of a kid that doesn't want to sit still. So these are actual movies. These are simulated movies of both M87 and SgrA with the clock running. And if you look very, very carefully, go back. If you go very, very carefully over a day, you can see a little bit of structural changes in M87. And that's because it's a monstrous black hole, and it's very, very far away. So anything that circles M87 takes a few days to make a change in its appearance. SgrA is in our own galaxy. It's a few million solar masses. So things that move around that change its appearance on the timescale of minutes. And if you understand a bit about radio interferometry, we were trying to build up these Fourier components while the Earth was rotating. But if the source is changing at the same time, we are basically left with very many unknowns to solve at the same moment. So between 2019 and 2022, we worked very hard to overcome these two fundamental limitations. It didn't help that it was also COVID, because our culture of collaboration, of getting together and building up algorithms by close collaboration, we had to completely reinvent it. But in the end, we had statistical corrections for the variability that we see not only here in the total flux, but also on some of our baselines, and for the interstellar scattering. And after we did all that, this is again how the raw data for SgrA looks like. You see these two minima, and because there are two minima, it has to be a ring. And in fact, from the relative height of the ring and the depth, you can figure out what the width of that ring is. So now you have earned another movie which we showed at ESO, at the European Space Agency. Oh, there's the music again. We have to switch to radio eyes, because otherwise we cannot penetrate into the center of the galaxy. This is the beautiful meerkat image, and we're going to zoom in on that. And in there is a sort of a spiraling gas stream, which is indicated of something happening at the center. And there's a special radio source we call SgrA, the compact source in Sagittarius A, and we got this. Okay, shall we have a quiz? I'll have a quiz question. Why was it rotating at the end? No amateur astronomers in this audience? Okay. It rotates at the end because... Oh, I don't want to go. It rotates at the end because the movie is in galactic coordinates, aligned with the galaxy, but we publish everything with north, equatorial north up. So at the end of the movie, you have to show that this is what we've been doing. So this was very, very tricky. It was very tricky to make an image of ZJ star. And we also wanted to be extremely cautious that we were publishing a robust result. So what we've done is not very standard in radio astronomy. We used 7 different imaging algorithms, 2 different calibration pipelines, and we used them in also in a blind challenge where we would make artificial data and give the artificial data to the teams and let them try to figure out what was the image in the artificial data. From that, we took the parameter space where it was most robust, and in the end, we also averaged, which is also very uncommon, we averaged our results over different algorithms. And so the paper that describes this is quite complicated, but I assure you it was not AI. We did it really ourselves, which is something we've been accused of. So here is a gallery of all, it's even better if you have 2 projectors side by side, of all the possible images that we got from different parameter settings and different instantiations of the noise and calibration factors. And we are very happy that there is a ring coming out when we average that together, but we are a bit more cautious in our papers to our peers, and we admit that there's not a single image resulting from our data, but there's actually 4 families of images which have different likelihoods of appearing in our analysis. So in the end, we published this, an image, but we carefully caution that the azimuthal structure is highly uncertain and our image diameter is only somewhat certain. Okay, so now we do interpretation in, oh dear. We do interpretation in 12 minutes. Now, let's see how far we get. So the interpretation is, we're looking here at a ring, and that ring is coming together because of hot plasma in the neighborhood of the black hole combined with the lensing. And you can imagine, for instance, here, so we use the Schwarzschild radius I've mentioned before, but what's important here is we are also using the Kerr metric, which allows the black hole to have spin. And you can imagine that depending on whether the black hole and the stuff around it are co-rotating or counter-rotating, the image will look quite different. And this was actually already studied early in the 20th century. And here are a bunch of formula. So let's go over them briefly. The gravitational radius is the m over d with the right constants. The Schwarzschild diameter, the diameter of the event horizon, beyond which nothing can return back to the universe, is at 4 times that radius. The last stable orbit on which things can rotate without being lost depends on the rotation of the black hole. If it's not rotating, it's about 12 times the gravitational radius. It can be larger if they are counter-rotating. And then there's something called the photon ring, and that is a ring imaged on the sky from photons or radio waves if in the direct vicinity of the black hole. And this is how that works. So some things come and only get banded, and we are imagining that our observing plane is here to the right. Some things are banded more. Some things get even bent around a full circle, or even 2 full circles. And this way you build up an image in the image plane that has a very distinct circle in it, which is convoluted by radiation from the surroundings, which is not as nicely precisely imaged. So let's see what we get in the end. So you see some emission from the surroundings directly, so that will depend on how the structure is of the accretion flow. You will see a shadow of the black hole. From the center of this image, nothing reaches the observer, and there's a ring on the sky of lensed image from the black hole. And one thing that most people don't realize when they look at this picture is this picture looks the same anywhere in the universe, right? There's no preferred perspective for us. We could have put that screen anywhere. So while you think that in the M87 image you were looking the monster onto the monster directly along the rotation axis, the circle actually occurs for observers in any direction. Well, there's a little caveat to that. I'll get to that in a second. What's my next slide? Okay, so now we can interpret the ZJ star image. So first I have to point out that we're doing radio interferometry and we're pushing it to the limits. Nothing smaller than that circle at the bottom is real, right? So everything what we see has to be taken into account that that's the resolving beam. Then there is the white circle. That is the very accurately known Schwarzschild radius for this black hole. Very accurately known because we know the distance and we know the mass from the stellar orbits. Then there is the magenta ring, which is where a material can still be in orbit without being lost to the black hole. And then there is the blue ring, where we assume that the photons get imaged into a ring. Now, if we have a good idea of what the surroundings of ZJ star look like, and if we have a good idea of what the spin is of ZJ star, we can make a prediction about the blue ring, and we can try to verify whether GR, general relativity, works in this regime. And beforehand, we would have assumed that we need to see something of 55 microarc seconds, which is exactly what we know. So, although the source is very variable, the azimuthal structure is very difficult to discern. There is nothing that points out that Einstein was wrong here. And some of my colleagues were very disappointed with that, because we're testing gravity here in a very strong regime and a parameter space where we have not observed before, and so some of us were hoping that new physics was to be uncovered. So to do the precise interpretation of this, and that's my last topic, general relativistic magnetohydrodynamics are extremely important. This way we are trying to build up a source model, which we can make subject to the same gravitational lensing and then to the same observing conditions that we had to test whether we have all our physics straight. So a large fraction of our collaboration of 400 people works on supermassive black holes in computers. They put out the vicinity of the black hole in a grid. They put in the black hole mass, the spin. They have configurations in which magnetic fields are very dominant and configurations in which they are less dominant. And they have different temperatures for electrons and ions. And they run simulations. And then in the end, we compare that to observations by scaling the distance and changing the inclination. And here's an animation of how that works. Basically, you have to set the mass of your black hole, and the free parameter is whether it spins maximally in the same direction as the surrounding material or in the opposite direction. And sorry, it's a bit slow in the beginning. I have more to explain than I actually have to explain. And we pick here a fiducial half, and then we let it run. And you get something like this, which actually blows jets, which is amazing because in SgrA we actually don't have a jet. And then you have to convolve that with a gravitational lensing, and you get something like this. And here you see that if you change the inclination, there's a little bit of a subtle difference. You get a more asymmetric view of a rotating black hole when you see it edge on, because some stuff is moving in your in the plane of your observations than when you see it face on. So we run millions of these simulations, thousands of these simulations for thousands of time steps, getting us to millions of images of what we should have seen. And we can use that to discriminate which models we think are the most likely. So here is a whole lot of these models running, and then we compare them, for instance, to the total flux, to the total size we measure, to the asymmetries, and the spectrum we measure at other frequencies, and we arrive at our preferred models for M87 and SgrA. And we use these models to calibrate the ring shape on the sky, because these models tell us what the relative contributions are of the n equals 0, 1, and 2 photons that you saw in that image. So we do this in very many ways, and we actually also take into account that different groups work on the stars in the galactic center, and we confirm with the SgrA image in size in this figure that there was nothing wrong with general relativity in this source. And we have two of these sources. They're very, very different, right? One fits into Pluto's orbit and the other is bigger than the solar system. And they both give us measurements of the scaling factor between the models and our observations, and they're both comfortably in the area, in the range of GR. Okay, so I want to stress here that we have been extremely lucky that we have been able to do this research. Not just because I'm not just thanking the taxpayers to make this possible, but we are really very lucky that we live on a planet that is just big enough to give us the baselines that we can resolve that that has an atmosphere that is just transparent enough that we can do it at the right frequencies, that we are just outside of where interstellar scattering could block it, and that we live in a time where we have the telescopes and the technology to do that. So it's really been quite fantastic in that sense. So what are we doing currently? So this is the paper that came out a few weeks ago. We have improved our telescope network, and we have improved our techniques. And so we have now not only stared at the data from 2017 all the time, we're trying to catch up with our quite incredible backlog. So this is how M87 looked in 2017, 2018, and 2021. You would expect, because gravity dominates and the mass of the supermassive black hole will not change on human timescale, that the ring diameter remains the same, and it does. So that's good. We also get much more reliable measurements now because we have more telescopes, so it's also confirming the robustness of our results. But what's sketched in here as well, and you see in tick marks in the middle row and in total relative polarization in the bottom, is that we're measuring the polarization of these rings nowadays. So the polarization is the footprint of the magnetic fields that are very important in the vicinity of the black holes. And although the ring diameter seems to stay the same, we see the magnetic field make substantial changes over the years. And so at the moment, what we're really pursuing is to do much more research into the dynamics of what's going on in the vicinity of black holes. So CJ star varies very rapidly, so we're trying to deal with that too. That's hard, but you will get some results about that soon. And next year we are actually going to spend a lot of time on M87 over a few weeks in a row to see if we can see the dynamics of the source. So all of that's possible because we keep adding telescopes to our network. We are also improving the technique so that even telescopes that are in low, bad atmospheric places, probably not Westerbork, probably not even Cambridge, but maybe some places in South Africa, for instance, can participate. And we are dreaming of a VLBI space mission which could resolve many more sources than we do now. And finally, I want to remind you that this is all the work of many, many very dedicated, multicultural, diverse community. It's been a privilege to work with these people. It takes you all over the world. Of course, we have collaborators in Spain, in Korea, in Hawaii, in Chile, in the US, of course, in the UK. It's been quite fantastic what innovations they have been bringing to this project. So that's where I conclude. Thank you very much. 23 seconds longer than an hour.
No worries about it. Now we can use the Q&A. So, any questions? Perfect. Let's start over there.
How confident would you be that there are indications of new physics from this data? Because it seems to not be very dependent and it's to do the reconstruction via simulations, but those simulations would be based on known physics.
Yeah. Okay. So we're trying to test GR in a parameter space. In parameter space of very strong gravity, and it cannot be done without some modeling of the magnetohydrodynamics that's participating. So I guess you are right. It's all a consistency check, right? And so far all the consistency checks seem to tick. Maybe I should point you to the reason why we are so cool about doing a space mission, because there it should be possible to resolve all the fluffy bit and actually see the rings very precisely. And for instance, shift of the ring would be an indication of the spin of the black hole. So that's where we want to push stuff. Nevertheless, I should also point out that there are enormous amounts of alternative physics theories for black holes that I don't claim to understand at all, but apparently we have closed out quite a number of these. What? Oh, okay, sorry, yes. So the Schwarzschild metric is for a non-spinning black hole, and there you can actually in the classic physics classic physics approximation work out what the Schwarzschild radius is. That's not the proper way to do it. You have to do it in GR, but you get the same result. The Kerr metric is telling you what the metric will be if the black hole is spinning, and you get some dragging along close to the black hole because of the spin of the black hole. So Kerr metric describes how the metric changes when the black hole is spinning. Sorry, yes. Are you asking very long baseline? Oh, yeah. Oh, do I want to do this? Get you all nauseous. Oh, yeah. Okay, so the diffraction limit of a single telescope, telescope like the Cambridge telescope, is very big. It's arc minutes on the sky, right? And so that arc minutes on the sky defines the area over which we have sensitivity. And that holds for all the individual telescopes. And as long as we point them all in the same direction, they all have sensitivity in the same part of the sky. And then the precise sampling of this complex correlation function with enough time and frequency resolution allows you to make an image of the very small patch on the sky. So you get to the diffraction limit of the whole array that way. So there's no conflict there. So you mean for the calibration of the data or for the calibration of the result? Okay, so we do two things with artificial data. We create artificial black hole images, and then we make a simulation of what our global telescope would have observed, and we use that to test whether the algorithms that we have produce the right result. But we also use the simulations to determine how this lensed ring will be blurred by the emission of the vicinity of the black hole. So we use the simulations twofold. Is that answering your question? Okay.
Yes.
Can you speak up because I
I can speak up.
oh yeah.
Quite futuristic here, but would it be possible, would it be better to have like telescopes in the moon or Mars because like there's no atmosphere, the atmosphere is
Yeah. So the moon would be great because there's no atmosphere, but the moon is too small, right? So ideally, you do this with a few space-based telescope, because then they all have no atmosphere, and we don't have to travel there anymore, and we just let the telescopes in space. That would be the best. But that's very expensive because then we have to launch 3 or 4 times.
Obviously, photo 2019 went quite viral online. As PhD director, how has like physics communication with people who aren't physicists outside of really helped with funding and
Yeah. You have to come to the bar if you want to hear that. So yeah, no, that's a very delicate process. So this was. I cannot claim we kept control over that all the way. In our collaboration, some big organizations appear at some point. ESO, the NSF in the US, NREO in the US, NOAJ in Japan. Big organizations that are used to doing that, and they quickly took over. And not everything went as smooth as you hoped, maybe. And in fact, it became at some point a bit disappointing how much they had sold our results already, leaving it very little for us to leverage to get more funding for what we want to do next. Yeah, it surprises you. It surprised me too a bit. Yeah.
Any more questions?
More of a question. Hey, what was the exposition time for the
The exposure type. Okay, so sorry I didn't mention that, but that's because most VLBI observations always use the same sort of observing time, because in 12 hours your telescope has rotated over all possible angles, so we always try to take as much of a single day as possible. Of course, the Earth is round, so you're not able to see with all telescopes the source every time. So usually an observation takes about 6 hours.
For the autocorrelation one, not the correlation one, how precisely do you need to know the position?
Okay, so that's a good question, and probably the others didn't hear. The question was, how accurate do you need to know the telescope? Well, it would be best if you know the telescope to a lambda, right? You're trying to find a correlation function, and you can calibrate it with some bright source on the sky. But if you want to go to another place on the sky, you want to be on the right lambda to detect it. So a fraction of a lambda is a fraction of a millimeter. And the other thing is, for a fraction of a millimeter, there's also a time. There's also a time that you have to register, which is equivalent to a fraction of a lambda over c. So you're having quite serious constraints on where your telescope is and how accurately you know what time it is. And these technical pictures are highly simplified, but a lot of these things are in place to make sure we measure all the round loops and calibrate all the a priori timing and position information very accurately.
But the telescopes were like never meant to be together, right?
Yeah.
So how did you measure the distance?
Okay. So you start with the measurements on a map. Then you ask the local geodesist to measure where your telescope is. And then finally what you do is you measure about 100 sources all over the sky, right? And you solve for the position of your telescope before you start this experiment, okay? This is how we know the plate tectonics, because this is how it was discovered that Earth is not so solid. Yeah. Oh yeah, we account for plate tectonics. We account for glacial rebound from the ice ages. We account for the gravitational influence of Jupiter when the wave propagates through the solar system. Yeah, all of that goes in.
Yeah, I got one more question. So in the final picture of the sector as A, so it seems there were like 3 blocks in a triangle.
Yeah.
I couldn't make my head around why is that triangle.
No, we don't trust the. We will tell you, you cannot trust the azimuthal structure. We are working on a paper that is trying to interpret how motion during the observations will affect the azimuthal structure, but I'm not allowed to show you any pictures.
Okay, one more question.
So you can get a what's the hardest
When we do the, sorry,
you have to account for things like what was the hardest thing to deal with?
okay, so all of that we've done for all VLBI arrays all the time. The real problem for the EHT is that the atmosphere above every telescope fluctuates on a timescale of 10 seconds. And so we normally calibrate that by making a detection within the fluctuation time. And so this is why only when we had the ALMA telescope we could start to calibrate the atmospheric fluctuations. And we've come up with quite a number of innovative tricks to deal with the atmospheric fluctuations. So all of that sounded really cool, what I just told you. The really hard part is atmospheric fluctuations.
One more round of applause.